Training the machine learning model is just the first step. The entire use of machine learning algorithm comes in when you use this model for predictive analysis. Before you apply the model, you want to save this trained model somewhere. How would you do that in TensorFlow? As a continuation from the last lecture, we'll predict taxicab demand in New York City. We've set up the dataset the way we want it to be. We'll now run the ML model on it. We'll train our model and then use it for prediction. You have some dataset on which you want to train your machine learning model. Typically, you would use a fraction of the dataset for training and the rest of the dataset to test or validate whether your model works. In this example, we use 80% of the data for training and 20% of our data as the test data, which we'll use to validate our model. We shuffle up our data set so it's not in any predictable order when we get started. This we do by calling the sample method or our data frame. We sample the entire data set, it'll now be in any random order. In our machine learning model, the variables that we use to predict the output, the predictor variable or the feature vectors, will comprise of the data, which is the day of the week, maximum temperature, minimum temperature, and the precipitation on any day. The target variable or what we want to predict is the number of trips. If you think about it, one of these features is a categorical variable, and that is the day of the week. This should typically be represented in one hot notation, where Sunday will be represented by a vector of 1 followed by zeros, Monday is 0, 1 followed by remaining zeros, and so on. Day of week is not really a continuous variable, but for simplicity's sake, in this model, we treat it as such. There is some code here in Google's Code Lab which allows you to treat the day of week as a categorical variable. It's not a great idea with a small data set because it leads to something called overfitting. When the day of week is expanded to the one hot notation, we increase the number of feature vectors that we pass in for prediction. When we increase the number of columns in the predictor variables, increase the number of features. If we have a huge number of features with a small amount of data, we can end up overfitting the model. Overfitting is when a model is very dependent or very sensitive to statistical error or noise and doesn't just define the underlying relationship. In this implementation, we'll treat the day of week as is, as a continuous variable which we know has just discrete values. The predictors for this regression are columns 1 through 5. These are the columns which are for the day of week, min temperature, max temperature, and rain. Let's quickly sample the shuffled data set. It's the same data we set up except in any random order. The target or what we want to predict in our machine learning model is the number of trips taxicabs take. In our training data set, this will serve as the training labels for our regression. The number of trips at index 5. We mentioned earlier that 80% of this data set is going to be used for training. The number of records that we have for training is stored in the train size variable. We'll compute a new baseline or a benchmark on our training data. Access the first 80% of rows from the shuffled data frame and find the average. The average calculation of the number of trips formed our baseline before. We are going to use the same thing for a baseline here. Once we have the average number of trips, find the root mean square error so we know how good this baseline is. Our training data set has an average of around 46,900 and a root mean square error of around 12,000. So, a prediction of around 46,900 cabs for a particular day can be about 12,000 trips away in either direction. If you've observed our data set, you'll see that the predicted value for taxicab demand is generally in the 10,000 to 80,000 range. These are very, very large numbers. We'll use all these number of trips values by scaling them down by a factor of 100,000 so that the resultant predicted values will be in the range 0 to 1. Machine learning models generally run faster when the weights that they use or the predicted values are smaller. We don't want to use these huge numbers. In order to speed up our model, we'll scale them down by a factor of 100,000. The next two lines of code set up 80% of our data for training and 20% for test. The number of predictors or regression variables in this model are the number of columns in our predictors data frame, which is 4. The number of outputs is just the number of trips for the taxi cabs. That is, number of outputs is equal to 1. Set the log level to 1 so we get fewer output messages. In TensorFlow, you can save your trained model to a directory. Now, the directory that we are going to use to save our trained model is this trained model linear. Remove the directory if it already exists. We don't want to load previous weights and biases from this directory. If this directory exists, then TensorFlow will try to initialize the model with data from this directory. We use a linear regressor, an estimator, to perform this regression. As we've spoken about earlier, estimators are high level APIs which take care of a lot of little details of regression for you. In the real world, the really common cookie cutter models, such as logistic or linear regression, you'll perform using estimators. There are some new parameters here that we haven't seen before. There is a model underscore dir, which is where we store our trained model. This is in the trained underscore model underscore linear directory under the current working directory. And here are some other inputs that we can specify to configure this estimator. The first of these is the optimizer that your estimator should use. If you don't want it to use the plain vanilla gradient descent optimizer, you can specify another one. Here we've specified the Adam optimizer. Ignore the enable centered bias argument for now. It's a way to specify whether you want the weights in your model to have a centered bias or not. And the discussion of this is beyond the scope of this example. And the last argument is the feature columns. What features you want this model to look at while training. Here is the input function, which gives the estimator information of the data set that it has to train on. A lot of the code that you see here is basically shaping the data to be in the right format and scaling the number of trips. Remember that we scale the number of trips down by 100,000 so that all our predicted values come in the range 0 to 1. This keeps the weights of the model low and helps it run faster. Pass in the input training dataset and the corresponding training labels. Call estimator.fit with the input function and specify the number of epochs for your training. When this line of code is executed, you have a fully trained machine learning model and you can use that model to predict taxicab demand. You can use this trained model to predict taxicab demand by calling estimator.predict. Here we do it for the test dataset. The test dataset is typically used to validate our model, and all the remaining data after the training data is the test dataset. In your final prediction, though, you need to scale up the output values by multiplying by scale num trips. You want the final result to be in the range 10,000 to 100,000 and not in the 0 to 1 range. Once you have the predicted values, you can calculate its root mean square error and see how well it performs. Our linear regression model using an estimator gives us a root mean square error of around 10,600. So, a little bit of an improvement over the baseline, the one we did calculating averages. Let's run a deep neural network regression model on the same data. And really, the only change you need to make for this is use tf.contrib.learn DNN regressor. That's the change in the estimator that you use. You've set up your dataset correctly, you can simply pick and choose your estimator. We don't need to go into the details of deep neural networks here, but you need to specify how many layers your neural network will have and how many neurons or nodes within each layer. That's where the hidden units comes in. Our neural network has 2 layers, 5 nodes in the first and 2 nodes in the second. Run the training for this regression model and you'll find that the root mean square error seems a little higher than what we got earlier. This is around 12,000 in my run of this code. Given the size of this dataset, and there could be many other factors which make neural network solutions harder to converge. We've stored our trained model in a directory. We can now use it to make predictions. Here is the input feature vector that we pass in order to determine what the demand for taxi cabs will be. If the days of week are 4, 5, 6, that is Wednesday, Thursday, and Friday, the minimum temperatures are 30, 60, and 50 Fahrenheit on those days. Maximum temperatures are 40, 70, and 60. And on Thursday, there's a little bit of rain. It says zero point 0.8 in our input. Instantiate a trained linear regressor from our model directory. Our model directory will have the weights and biases for the neuron that goes into this linear regressor. We have the estimator instantiated. We can call estimator.predict in order to get our predictions. The predictions need to be multiplied by scale num trips so they are in the right range. Run this bit of code, and there you'll see the result. If you remember our visualization earlier, Thursdays tend to be slow days. The demand on Thursdays tend to be much lower than on Fridays. But here, they're almost the same, 47,000 as opposed to 49,000. This may be because we've set it up so that it has rained a little bit on Thursday. The demand for taxi cabs is higher. If you've trained a machine learning model, how would you save it to use it for future predictions? You would specify a model directory when you set up an estimator, and the estimator will simply write out the weight and bias values in that directory. Using a trained model for predictions simply involves instantiating your estimator. In our case, it was a linear regressor by pointing to the model directory.